Welcome to the last video on circular motion, and in this video we're going to be looking at circular motion still, but just some things that are a little bit different. We're going to be looking at the universal law of gravitation, which technically some instructors cover this in unit 4 and 5 in the first semester, but it does come into play here as well since we're looking at satellites going in circular orbits. So to start us off, let's go ahead and look at the universal law of gravitation equation-wise, and then understand what it's actually telling us. All right, so the universal law of gravitation states that force is equal to capital G times m1 times m2 divided by d squared. And sometimes the equation sheet has r squared instead of d squared. It is essentially the same thing. So you'll see it in two forms. Now, what the heck does that even mean? Before we get into what the variables are, let's understand what universal law of gravitation is telling us. What it's telling us is any two objects that have mass will be gravitationally attracted to one another. And that's kind of interesting to think about, because when we think about gravity, what do we normally think about? We normally think about how we, being object 1, are attracted to object 2, being the Earth. We're attracted to the Earth, we're drawn towards the Earth. That is definitely true, but that is not the only example of gravitation. Any two objects actually have gravitational attraction towards each other. For example, you are attracted to the computer screen or phone that you're viewing this video off of. You are attracted gravitationally towards that device, and likewise that device is gravitationally attracted towards you. You're also attracted to the door that's in the room. You're attracted to maybe that pen or pencil that's sitting in front of you. You're attracted gravitationally to everything that has mass, which is really an astounding thing to think about. But the reason why you don't feel it is because the mass of the two objects, you and the pencil or you and the door, are so small relative to, let's say, the mass of the Earth. And so while you do experience a gravitational force, it's not large enough for you to actually see it. But nevertheless, there actually is a force of attraction, and using this equation, we can actually calculate what that is. So we can calculate force by taking, first of all, capital G. Please note this is a capital G, not a lowercase g. So when you're using this equation, this g is not 10. Instead, it has the value of 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. Now it has those funky units because the meters squared will get canceled out when you have this distance squared, and the kilograms squared will cancel out when you take your masses and times them by each other. So essentially the only thing that would be left is newtons, and that's what force is measured in. All right, m1 and m2 are the mass of object 1 and object 2 respectively. And then d is the distance that is between the two objects. Do not forget to square it. That is a commonly missed thing on these types of problems. Okay, the masses need to be in kilograms and the distance needs to be in meters. Knowing that, let's look at a sample problem. All right, it says, determine the force of gravitational attraction between the Earth, whose mass is 5.98 times 10 to the 24th kilograms, pretty big, and a 70 kilogram student that is standing at sea level, and the distance of the Earth's radius is 6.38 times 10 to the 6th meters. So let's draw a picture here. All right, so we have our Earth, and on top of our Earth, we have our physics student. Now, obviously, this is not drawn to scale because a physics student is not that ginormous, but just to get the idea. Now, our mass 1 is going to be our physics student mass, and our mass 2 is going to be the mass of the Earth, which is 5.98 times 10 to the 24th. Notice both of those are in kilograms, so we do not need to convert. Now, g is a constant, so the only thing left is we need to know what's the distance between them. Now, to a student that is still learning this for the first time, they might be tempted to say, well, wait, if the student is standing on the Earth, isn't the distance 0? Because there's no distance between the person and the Earth? Well, that answer is wrong on two levels. First of all, the distance in this formula is going to be the distance from the person to the center of the Earth. After all, what you're actually gravitationally drawn towards is the actual core of the Earth. That's where most of the mass of the Earth actually resides. And so The distance that gets plugged into the equation is that distance between the person and the center of the Earth, which the problem tells us is 6.38 times 10 to the 6th meters, which is nice because it's already in meters. We don't have to convert. Now, I told you it was wrong on two levels. The second way it's wrong is there's always distance between two objects. Even though it looks like from our level there isn't, there is. For example, you are sitting on a chair, most likely. If I ask you what's the distance between the chair and you, from a macroscopic view, you would be tempted to say 0. There is no distance between you and the chair. But in the microscopic, very, 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 very microscopic world, there actually is a distance. Oh, it's very, very, very tiny, but there actually is a distance. So there's never going to be a distance of 0 between two objects. The only time that would be 0 is if it was just one object. And that's not what you're doing here. So anyway, that's kind of a little tangent there. Let's come back to the problem and let's solve this. So we have our two masses. We have our distance. They're all in the right units. So now all we have to do is calculate. So the force is going to be the gravitational constant of 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared times 70 kilograms times 5.98 times 10 to the 24th kilograms, and that is all divided by our radius of 6.38 times 10 to the 6th meters, and then do not forget to square it. That is a commonly missed thing. All right, the hardest part about doing this problem right here is not the physics, because the physics is done. It's the algebra, and it's the using your calculator. When you're dealing with things in scientific notation, please make sure on your calculators that you are using the EE button. Most students' calculators have this either as a button or as a second command. If you're using a TI-83, you'll notice that this command is the second function of the comma button. And I know that's a lot of students, but if you're not, most students have this button. Sometimes they have the EXP button, or they'll have the times 10 to the X button, or times 10 to the Y, or times 10 to the something. But most students hopefully have the EE button that is written first. You will punch that in for the times 10 part. Okay, so when you're typing that in your calculator, we're going to do 6.67 E, and then type in the exponent, negative 11th. Make sure when you type in the negative 11th, do not type in the subtraction symbol for the negative. You need to actually use the negative button. All right, so 6.67 times 10 to the negative 11th times 70 times 5.98 E 24. And that gives you 2.79 times 10 to the 16th on the top. Then on the bottom, we are going to divide it by 6.38 times 10 to the 6th squared. And if you do that correctly, you should have gotten a force of 685.9 newtons. Okay, the last slide, and this will complete the video, is how do we use this idea of gravitation in space to do circular motion? The most common thing that we're talking about here is satellites. So we think about all the satellites that are orbiting around the Earth, and I think there's roughly about 3,000 satellites that orbit the Earth, which is really crazy to think about. How do we actually get them up there, and how do they move? Well, look at the picture on the left. Kind of an exaggeration. We don't have a man or a cannon that large, but you can kind of see the idea. We need to actually shoot satellites into orbit with the right trajectory and the right velocity in order to keep them in circular motion. So you can see there that if we don't shoot it with enough velocity or trajectory, you can see that they will actually fall right back down towards Earth, and they will crash into Earth. It's only when you get just the right trajectory and just the right velocity that the satellite, or in this case the cannonball, gets itself to a point to where it wants to keep falling towards the Earth, but it can't. It's always in this state of free fall, but it never quite gets to the Earth's surface, and it just keeps going and going and going. So if I were to draw a force diagram for the satellite or for the cannonball at any point, it would always just be force gravity, and force gravity would always be pointing towards the center of the circle. Whether it's here, or anywhere, it'll always face towards the center of the circle. And so the centripetal force of the satellite really is just coming from the force of gravity. You can see on the right-hand side, there is a kind of a glimpse shot or a time shot of a satellite as it moves from 1 to 6 around the Earth. So as it's going around the Earth, the satellite wants to keep moving in a straight line. For example, when the satellite's right here at the beginning, it wants to keep going in a straight line because of Newton's first law, or law of inertia. But force net forces it back into the circle. Same thing here. It wants to keep moving in a straight line, but force net pushes it. And same thing here. Force net pushes it. It keeps pushing towards the center of the circle. What is pushing the satellite towards the center of the circle? Remember, it's gravity. The Earth is pulling the satellite always towards itself, but the satellite is never reaching the Earth because it's always in a state of free fall. All right, this completes not only the 4th video lesson, but also the entire unit on uniform circular motion.